I'm Sudarshan Lamkhede. I'm applied researcher at Netflix Research, and I'm very thrilled to announce our next keynote speaker, Professor Chelsea Finn. Chelsea is an assistant professor at Stanford University in the Department of Computer Science and Electrical Engineering. And her research interests include how the capability of robots and other agents to develop broadly intelligent behavior through learning and interaction. To this end, her work has included deep learning algorithms for concurrently learning visual perception and control in robotic manipulation skills, inverse reinforcement models for scalable acquisition of nonlinear reward functions, and meta-learning algorithm that can enable fast, few-shot adaptation in both visual perception and deep reinforcement learning. Chelsea received her bachelor's degree at MIT and her PhD in computer science at UC Berkeley. Over her career, she has earned quite a bit of accolades, including ACM Doctoral Dissertation Award, Microsoft Research Faculty Fellowship, the C.V. Ramamurthy Distinguished Research Award, and the MIT Technology Review 35 under 35 award. Throughout her career, she has sought to increase representation of underrepresented minorities within computer science and artificial intelligence by developing an AI outreach camp at Berkeley for underprivileged high school students, a mentoring program for underrepresented undergraduates across 4 universities, and leading efforts within the Women in ML and Berkeley VI computer science engineering, women in computer science and engineering communities of women researchers. Today, her talk is titled Meta Learning for Robustness to Changing World, and she is going to discuss how we can allow deep networks to be robust to such distribution shifts via adaptation. She will also focus on meta learning algorithms that enable this adaptation to be fast. First introducing the concept of meta-learning, and then briefly overviewing several successful applications of meta-learning, ranging from robotics to drug design, and finally discussing several recent works at the frontier of meta-learning research. Again, the talk is by Dr. Chelsea Finn. Let's start the stream soon.
Hi everyone, my name is Chelsea Finn. I'm an assistant professor at Stanford, and I'm going to be talking about meta-learning for robustness to our changing world. The motivation behind this talk is that there's currently a gap between the paradigm in which we do machine learning research and our current reality. So at least in machine learning research, there's a paradigm of taking a training data set, developing an algorithm that trains on that data set, trains a model on that data set, for example, and then evaluates that static model on some test set, on some benchmark, and then we call it a day. That's kind of how we evaluate our algorithm. But in reality, the world is constantly changing between stocks, between varying supply and demand over time, or even robots that are encountering different parts of the world. In reality, machines are constantly seeing new things and constantly seeing different parts of the world or parts of the world that have changed from when they were trained. So we have this gap between evaluating static models that were trained on a data set from one point in time and our reality where the world is constantly changing and those static models won't work well when things are changing. So how can our algorithms handle the changing world? Well, one place where we might look for some inspiration is industry. So machine learning has been pretty successful in industry. How does industry cope? Well, let's ask Chip Huyen. So if you ask Chip Huyen, who works on machine learning in production, she would tell you that machine learning systems degrade very quickly because of concept drift. And for online machine learning systems, you want to update them as fast as humanly possible. So clearly, the way that our machine learning techniques are being used is not the way that we intend when we're doing research and developing these algorithms. And if we could figure out how to actually develop them such that they're used in the way that we intend, maybe we'd be able to make machine learning even more successful in industry, especially in settings where things change constantly. So how do we go about solving this problem? One solution is to widen the training data in the hope that the way that things change will fall under this wider distribution of what we might be training on. And there are a couple of ways to do this. One simple way is just to acquire more data, but we could also try to build algorithms that have better data scalability. And by that, I mean the ability to leverage widely accessible data sources, such as unlabeled data or data from other domains that might be more accessible than the domain that we ultimately care about. And this approach works great. So for example, if we look at GPT-3, if you ask it very kind of reasonable common sense questions, it can give you the correct answer, like that a giraffe has 2 eyes and a frog has 4 legs. However, these approaches also seem to have their limits. So if you ask them questions that are maybe a bit different than the things that they may have seen in their training data, like how many eyes does my foot have, or how many eyes does a spider have, they won't quite give you the correct answer. So clearly this isn't kind of the only solution for actually deploying algorithms in the real world. Another solution that I think is probably the kind of common practice in industry is to continuously fine-tune your model when that is applicable. And this also works great. So we've seen massive successes in computer vision when you pre-train on the ImageNet dataset. We've also seen substantial gains in natural language processing when you pre-train on the language modeling task and fine-tune on some target dataset. And more recently in robotics, we've also found that fine-tuning can be quite successful even in the context of reinforcement learning algorithms. So we took a state-of-the-art robotic reinforcement learning system that is trained to grasp objects that has a success rate of 86%. Unfortunately, when things change, such as when you use drastic lighting, have kind of harsh lighting conditions, transparent bottles, a checkerboard background, or a pretty large change in the morphology of the robot gripper, the performance notably gets worse. But if you fine-tune on a modest amount of data, you can get substantial gains and sometimes actually recover performance that is similar or even better than the original performance. So fine-tuning works really well at adapting to distribution shift. But of course, it also has its limits. So it requires a non-trivial amount of labeled data and a non-trivial amount of computation to fine-tune a model. So what I'd like to talk about today is whether we can introduce assumptions that allow us to generalize further with less data. And the goal will be to make these assumptions mild, but also powerful. And a core tool for accomplishing this will be the tool of meta-learning. With that in mind, I'll first give a brief overview of meta-learning and what it's currently capable of, with a few kind of examples of what people have done with meta-learning in the past year or two. I'll then talk about whether we can capture equivariances with meta-learning to allow us to generalize more effectively, and whether we can fine-tune without any labeled target data and use meta-learning to adapt to distribution shift with fewer assumptions than what fine-tuning gives us. But first, let's give an overview of meta-learning. So I'll start with a canonical example of the few-shot image classification problem. And what this looks like is we're given a tiny training data set of just 5 examples, where we have one example of 5 different classes, and our goal is to do one-shot learning, where we want to be able to classify new examples as being among one of these 5 classes on the left. So essentially, we want to be able to learn and generalize from this tiny training data set. Of course, if you train from scratch on this tiny data set, you wouldn't be able to do very well. And even fine-tuning typically isn't able to generalize from such a small number of examples for a new target task. So the way that meta-learning works is it tries to structure image data from other image classes to prepare the model for this few-shot classification problem at test time. So it structures image data into mini train sets and test sets and trains the models on these training classes such that after it's seen one of the training data sets, it can effectively generalize to the test data points. It's essentially learning how to quickly learn each of these meta training tasks, such that when it's given one of these new test tasks at meta test time, it's able to generalize with a very small amount of data. It's essentially matching exactly what's happening at meta training time and meta testing time, lifting the learning problem up a level such that we can generalize with a very small amount of data. And of course, this problem setup isn't specific to image classification, so you can replace these image classification tasks with things like regression problems, language generation problems, skill learning problems, or really any machine learning problem. This is a way to enable few-shot learning by giving the algorithm examples of many few-shot learning tasks. So how do algorithms actually solve this problem setup? There are two kind of common classes of approaches that I'll briefly talk about. The first class of approaches is to parameterize your learner with a neural network. So you essentially take your training data set, feed that training data set into a neural network, which is representing kind of a learning process, and then give that neural network one of the unlabeled test examples and train it to accurately predict the corresponding label. So you're essentially training this network from scratch to learn from data and use what it's learned to accurately make predictions. And this neural network is, of course, trained end-to-end with respect to the accuracy on the test examples for each of the tasks in your meta training set. And then a second approach is to try to build a little bit more structure into the inner learning process. Rather than using a black box neural network, it tries to embed an optimization process inside that meta learner. So we might have a set of initial weights. We'll take our training data set, run an optimization on that set of initial weights to get an updated set of weights, and then train this optimized set of weights to be able to, again, make predictions on the test set. And then what the meta learner is doing is it's optimizing any free parameters of this inner optimization process. So for example, the model agnostic meta learning algorithm, or MAML, optimizes for a set of initial parameters such that a few steps of fine-tuning allows you to generalize from a small number of examples. Essentially trying to learn for an initialization that works especially well with fine-tuning. Okay, so to give a little bit more intuition for the second class of approaches, and specifically the MAML algorithm, we'll actually look at a quick reinforcement learning example where we trained a set of initial parameters such that fine-tuning is very fast and efficient for training an agent, adapting an agent to run in different directions. And first we could look at what the policy that it learns looks like after the meta learning process, but before it's adapted to any of the different tasks. And we get a policy that looks like this, that's essentially running in place. It's ready to run or adapt to any given direction. If we then take one fine-tuning step with respect to the task of running forward, we get a policy that looks like this, that can, just with a single gradient step, adapt its behavior quite drastically. And if we take one gradient step with respect to the task of running backward or to the left, we get a policy that looks like this. That's also, again, very able to quickly adapt its behavior to something completely different. So this is some intuition behind how these meta learning algorithms work. What have they enabled more recently? So I'll give 4 different examples here of examples of how meta learning can allow you to adapt models quickly to new situations. So in this first example, we wanted to see if meta learning can be used to quickly adapt a robot to new objects that it may encounter in the world. And so different tasks correspond to manipulating different objects, specifically for imitation learning. And the algorithm corresponded to the MAML with a learned inner loss function. And at test time, what it was able to achieve is we gave it one demonstration of a video of a person completing a task, in this case, placing the peach into the red bowl. And then as a result of this, it's able to learn a policy that can generalize to new positions of the bowls, just from a single example. So we're able to successfully adapt the policy to a new object that it hasn't seen before. Okay, Another work actually from this year looked at whether models can be quickly adapted to new molecules. So this may have applications towards low resource drug discovery problems. Different tasks corresponded to predicting properties and activities of different molecules, and they evaluated a number of different gradient-based metal learners, including mammal, first-order mammal, and almost no inner loop, which adapts only the last layer of the mammal model. And they used a gated graph neural network as the base architecture. And what they found is because they are only adapting with a very small amount of data, they're able to significantly outperform approaches that use fine-tuning by leveraging meta learning over other previous molecules. In the third example, we looked at whether models can be quickly adapted to new terrains and conditions. In this case, we were looking at a legged robot that may encounter different parts of the world over time. And different tasks corresponded to modeling the robot dynamics across varying terrains and varying conditions. So for example, here's some videos of the different terrains that we trained this robot on. And the model was mammal across time, across kind of its past experiences, training it such that after it saw a little bit of experience from one environment, it could quickly model the dynamics in that environment. And then at test time, we wanted to adapt the model very quickly to a scenario where it didn't have a leg. So we took off the front right leg of the robot, and the robot actually had to adapt online in real time to less than a second of experience in this new situation. And as we can see here, the robot is able to accurately adapt its model, its dynamics model, to this situation where it's lost its front right leg, and use that dynamics model to plan to walk in a straight line. Okay, and then as a final example, this recent work looked at how models can be quickly adapted to new regions of the world. An example where you may want to deploy a model in a scenario that's a bit different than the regions that it saw previously. And they're specifically looking at the problem of land cover classification, where you want to be able to segment or classify the land cover for different regions. So they took two different data sets shown here, one with coarser labels and one with finer labels. As you might imagine, collecting labels for this kind of data is very tedious and expensive. And so we want to be able to adapt to new regions with just a small amount of data. They took the mammal model in this case, but of course adapted it to this problem setting. And what they found is on both of these two data sets, they're able to significantly outperform a model that's just pre-trained and fine-tuned to these tasks, and also a model trained with random initialization by using meta learning across these different regions. So essentially, meta learning is able to prepare it to quickly adapt with a very small amount of data, where the x-axis on each of these plots is showing the number of data points it's able to receive on the test region. Okay, so that's kind of a few examples of what meta learning is currently capable of and how it can allow us to quickly adapt to changes in the world or changes in the task. Now I'd like to talk about two recent works that try to push meta learning even further to allow us to generalize further or with fewer assumptions. So first I'll talk about, can we capture equivariances with meta learning? And the motivation behind this is that there's actually a third solution to distribution shift beyond just collecting more data and fine-tuning. And this solution is to build structure into your model or into your algorithm to help the model generalize. So as a concrete example, if we build in translation equivariance into our model, this will allow it to generalize more broadly to translations of your data. So this is great when we know the structure and we know how to build it in. For example, a translational equivariance and a few other forms of equivariances. But it's not great when we don't know how to build it in, or we don't know what the structure exactly should be for our scenario. So what we wanted to ask in this work is if we can discover equivariant and invariant structure via meta learning and use that to build it into the model such that our model can generalize further from the data that it's given at test time when it's trying to adapt. So first you might ask, well, does meta-learning already do this? Does like an algorithm like MAML already capture things like equivariances? And in some ways it can. So MAML can learn initial parameters such that the features are equivariant, but that equivariance may not be preserved in the gradient update. So you may not actually end up with a model that is actually equivariant, where that equivariance is retained throughout the process. So the goal of this work was to try to decompose the weights of a neural network into the equivariant structure and the corresponding parameters. And if we can do this decomposition, then we can update only the parameters in the inner loop and retain the equivariance. And by retaining the equivariance, we should be able to generalize a bit further. So to think about how we might do this, we can look at first how equivariances are represented in neural networks. So let's look at an example. So we can take the example of convolutions, a 1D convolution layer, for example, where we have some filter weights shown here, the input and the corresponding output for applying this filter to the input. And it turns out that this 1D convolution layer can also be represented as a fully connected layer that looks like this. So again, this is the weight matrix. You can see this weight matrix has a certain structure where the filter is repeated along the diagonal of the weight matrix, and the rest of this weight matrix is 0. And this represents the same exact function as the convolution function on the left. And you can also see in this example that it produces the same output. Okay, so this is pretty cool. So this means that we can represent things like convolutions as fully connected layers. And what it means is that it gives us a way to potentially reparameterize this weight matrix in a way that separates out the structure and the underlying parameters. So the key idea here is we're going to reparameterize the weight matrix to separate out the underlying filter parameters and the sharing matrix, which tells us how these underlying parameters should be repeated and shared within our overall weight matrix. So we'll take the matrix vector product of these two things. This will give us a vector, and we can then reshape this vector into the shape of our weight matrix. So essentially, this reparameterization allows us to give one matrix that can capture symmetries and one vector that can capture the underlying shared parameters. The sharing matrix doesn't need to be binary. It can also be continuous, which is useful in settings such as 45-degree rotation, where you may need to interpolate to some degree. And theoretically, we can show that this reparameterization can directly represent a decoupled equivariant sharing pattern and filter parameters for all group convolutions with a finite group G. There are kind of a large number of group convolutions with finite groups. This covers a number of different kinds of rotations, translations, permutations, and so forth. This is quite nice. It doesn't mean that we're guaranteed to capture this kind of separated symmetries and underlying shared parameters, but it's nice in that it shows us that we are capable of representing these separately. Okay, so now that we have a way to separate out the sharing pattern and the underlying parameters, we can then, in the inner loop, only update the parameters and keep the equivariance, the symmetry matrix fixed. And then in the outer loop, learn the equivariance from our set of tasks, as well as the initial parameters v. So what this looks like is this diagram right here, where the first row is showing the inner loop loss that's adapting only these underlying parameters v using that inner gradient and keeping the symmetry matrix u fixed. And then we will evaluate our test examples using these updated filter parameters and the fixed equivariance and the neural network that corresponds to these kind of weight matrices that are reparameterized by both of these. Now, one key assumption that this is making is that the symmetries that we want to be able to capture have to be shared by all of the tasks. And if they're shared by all of the tasks, that means that it could potentially represent those symmetries in U. It may also represent other shared things in U as well, depending on how much your tasks share. Okay, so we refer to this approach as meta-learning symmetries by reparameterization, or MSR, somewhat self-explanatory. Now let's get into some of the experiments. So our first hypothesis was that with this approach, perhaps we'll be able to recover 1D convolutions from translationally equivariant data. To study this hypothesis, we generated some synthetic tasks that were basically random 1D or random translationally equivariant functions, and kind of ran various meta-learning algorithms across these functions. And in particular, we evaluated MAML with different underlying architectures with a fully connected, locally connected, and convolutional architecture. And we also evaluated MSR with fully connected layer weights W, which are, of course, reparameterized with the MSR approach. And what we found is that MSR with the fully connected network was able to match the performance of MAML with convolutions in this example, suggesting that it's able to capture things like translation symmetry. And both of these are, of course, able to significantly outperform MAML with fully connected networks and locally connected networks because they aren't able to capture and keep this equivariant structure fixed. And further, beyond this, we found that if you visualize the recovered weight matrix, we get something that looks exactly like a convolution, where you get this these repeated weights along the diagonal and sparse weights everywhere else, suggesting that we are able to recover 1D convolutions from translationally equivariant functions. Now, can we recover something better than convolutions? So for example, what if we have data that doesn't have full translation symmetry, but only has partial translation symmetry? And in particular, we can take some locally connected layers or locally connected functions that have low rank, like a small number of underlying filters that make up those locally connected networks. In the case where the rank is 1, then you just have one filter. This just directly corresponds to convolution. In the case where you have 2 or 5, this means that you have a partial translation symmetry that convolutions won't be able to capture. They'll assume that you kind of have full translation symmetry. And what we find in this case is that MSR with fully connected networks is able to recover this partial translation symmetry and do significantly better than MAML with convolutions when you only have partial translation symmetry. And then finally, with these synthetic experiments, we also looked at data that has translation, rotation, and reflection symmetry. And in this case, we actually applied MSR on top of a convolutional architecture. So we're building in the translation equivariance in this case, which is nice because we already, in many situations, we may already know that translation equivariance is reasonable. And find that we're able to recover rotation and reflection symmetry using MSR, while MAML with convolutions isn't able to effectively capture that structure in the data. Great. And then finally, we looked at non-synthetic data. So we looked at the OmniGlot and ImageNet datasets, or mini ImageNet datasets. And in particular, we wanted to see whether we could try to bake in augmentation into the architecture or into the update rule. And this is motivated by scenarios where maybe like you have a sim-to-real transfer problem or other problems where during meta training you can access augmented data, but at meta test time you are only able to adapt to data that doesn't kind of explicitly show all of the kinds of equivariances that you think it will be able, that doesn't exhibit all the kinds of equivariances that you want to be able to generalize to when you adapt to that data set. So what the training procedure looks like is we assume that we have the ability to augment data during meta training. So we take a training set and a test set for each task. We then augment only the validation set for that task, and then basically train a model such that after it's adapted to an unaugmented training set, it can generalize to an augmented validation set. And what we find is that across the board, for both OmniGlot and mini ImageNet, MSR is better able to capture the symmetries implicit in a number of forms of data augmentation compared to mammal and almost no inner loop. And we also find this able to perform kind of on par with prototypical networks in the case of augmented omniglot, and substantially better than prototypical networks in the more challenging augmented mini ImageNet case. Okay, so essentially this provides us a way to capture symmetries that allow us to generalize further to augmented data, for example, from data that hasn't been augmented. And it also provides a framework for understanding the interplay of features and structure in meta-learning, because it shows us how if we allow the model to fix part of the parameters in the inner loop, that allows it to retain the structure and potentially generalize further as a result. Now I'd like to talk about, beyond kind of trying to generalize further, can we fine-tune with fewer assumptions on the fine-tuning process? So oftentimes it's maybe a bit too much to ask to have labeled data to be able to adapt at test time. In all the methods that we've talked about so far, we reduced the amount of data that we needed to adapt, but we still needed labeled data. So can we fine-tune without any labeled data? In this work, we'll specifically consider a form of distribution shift called group shift. And what I mean by this is that there's this categorical group variable z that underlies our data. This could be things like the user, the location, the time of day, and can typically be derived from metadata in a number of different cases. And we assume that the training data is drawn from a distribution like this, and the test data is drawn from a distribution like this. So basically there's this underlying variable z, and the distribution over z is going to change. And this can capture things like label shift. It can also capture most forms of covariate shift. And it captures problems like federated learning, for example, where you want to adapt to a new user that you haven't necessarily seen before, and the users that you trained on may be a bit different. So one approach for handling group shift is what's known as group distributionally robust optimization. And the way that this works is that you essentially form an adversarial distribution over the variable z. And then kind of optimize with respect to that adversarial distribution. So in particular, what this would correspond to is optimizing for the worst case group during training time. The benefit of this approach is that it can enable robust solutions, and is also often less pessimistic than adversarial robustness. So it often won't sacrifice overall performance quite as much in comparison to things like adversarial robustness, where you're trying to protect and be robust to all sorts of perturbations within a certain fault. The downside of this approach, though, is it still often sacrifices average and empirical group performance to some degree. It's still somewhat pessimistic about the kinds of groups that you'll see at test time. So what we wanted to think about is whether we can adapt to distribution shift instead of aiming for robustness, and specifically adapt using unlabeled data. So at test time, we'll assume that we have unlabeled data from some sub-distribution at test time. This could be a new user, a different time of day, a new place. And for example, in the case of this federated extended MNIST dataset, where you have all sorts of characters written by different users, you may have some unlabeled examples of how that user writes different characters. And then you want to be able to leverage this unlabeled data to both adapt your model and ultimately infer the labels for these unlabeled examples and other examples. So one assumption that we're kind of implicitly making here is that at test time, you have example unlabeled inputs from one group available either in a batch or in a streaming setting, such that you're able to kind of accumulate a modest number of unlabeled data points from that part of the distribution. And I think that this assumption is fairly mild, because in often cases you are actually observing data from a certain time of day or a new place or a certain user, or you have that metadata available. So we refer to this framework as adaptive risk minimization in the sense that we're actually training for the kind of, we're optimizing for performance after we've had the opportunity to adapt to different parts of the distribution. And the way that it works at training time is we simply construct sub-distributions of the training data and train for adaptation to those different subdistributions, so that when we're given a slightly different subdistribution of the data, we're able to adapt. So now, how do we actually train models that can adapt with unlabeled data? It's actually quite simple to adapt existing meta learning algorithms to the setting of adapting with unlabeled data. So one approach is to use MAML with a learned loss function. So of course, if we only have unlabeled examples, we can't evaluate things like cross-entropy loss or something, but we can actually learn a loss function such that when you train a model with a few steps of gradient descent, using that loss function, you get an adaptive model that can perform well on these examples. So that's one approach. Another approach is to use meta-learning with a context variable. This is a bit more similar to the black box approaches that I mentioned before, where you take a network that processes the unlabeled examples, produces a context, and uses this context to make predictions. And in one kind of one of the simplest cases, actually, or in one of the simplest instantiations of this kind of architecture, is to just have the context be batch norm statistics, where you're basically computing the batch norm statistics on your group of data and using those statistics when processing the test example. Now, importantly, this doesn't correspond exactly to standard training with batch normalization. This corresponds to specifically grouping your data or sampling mini batches into these kinds of groups and training it such that when you compute these batch norm statistics within these groups, you can make predictions effectively. Okay. So experimentally, we compared this kind of adaptive risk minimization framework to standard empirical risk minimization, to distributional robustness, and also to empirical risk minimization, but where you upweight the groups to the uniform distribution in cases where you have groups that are kind of unbalanced. And we compared 3 different architectures for adaptive risk minimization, including adapting with context variables, adapting with context variables that specifically correspond to the batch norm statistics, and adapting with a learned loss. And in the federated MNIST scenario that I showed before, we are specifically trying to adapt to new users with only unlabeled data. We additionally compared to this Q-Fed-average method that represents kind of a state-of-the-art in federated learning. And we find that if we're comparing adaptive risk minimization to these prior approaches, we get a 5% improvement in average accuracy, which is a pretty significant gain. And we also get a 10% improvement in worst case accuracy, where in this case, worst case accuracy corresponds to the worst user at test time. And this is something that you might care about if you are ultimately kind of deploying models for different users and you don't want some users to have a terrible experience and some users to have a great experience. It instead allows you to kind of optimize for more even or better worst case performance means that you're getting a more even performance across users. Okay, and then qualitatively, what does this actually look like? So say you want to classify this example down here. This is a bit ambiguous between a 2 and a lowercase a. And in fact, empirical risk minimization classifies it as a 2. If you give adaptive risk minimization with a contextual meta-learner these 2 examples, so essentially this image and this E right here, it also predicts that it's a 2 because this E doesn't give it that much more information about the user. But if you give adaptive risk minimization all of these examples, it's able to look at other 2s and other A's in the data set. These are all unlabeled examples, and it's able to figure out that this user writes 2s a little bit differently, and it correctly classifies this image as an A. So this is an example of how it can adapt to different parts of the distribution using unlabeled data. Finally, we took the CFAR-C and the tiny ImageNet-C datasets. We were trying to adapt to new image corruptions in these datasets. So we're training using 56 of the corruptions and testing using 22 disjoint corruptions from what we're seeing during training. And we again see a pretty big gap in performance by allowing these models to adapt with unlabeled data. So we see a 3 to 10% improvement in average accuracy and an 8 to 21% improvement in worst case accuracy, with 8 being 8% improvement on tiny image.c and 21% improvement on CFAR10C. So this is pretty substantial. Okay, so to wrap up, if you take away nothing else from this talk, I'd love you to take away the fact that we have this huge gap between our current paradigm in machine learning research and our current reality, where we're in this paradigm where we evaluate static models, and in reality, the world is constantly non-stationary, and we should be thinking about how our models can adapt to that non-stationarity in the world. I talked about how meta-learning is a tool for enabling very fast adaptation with a small amount of unlabeled data. I talked about some preliminary evidence that showed how meta-learning can capture equivariances in the data to allow you to generalize a bit further. And I also talked about how we can use meta-learning to quickly fine-tune with only unlabeled examples from a part of the distribution via adaptive risk minimization. With that, I'd like to thank my students. I'd specifically like to thank my students and collaborators who were deeply involved in the work that I presented, including Alan, Tom, Marvin, Henrik, Nikita, and Sergey. If you're interested in learning more about meta-learning, multitask learning, and generalization, all of the lecture videos for my course on meta-learning are available online, and I'd be happy to take your questions. Thank you.
Thank you very much for a very fascinating talk, Professor Chelsea. We are now open for the questions and answers. We already see some here. I'm going to start with the first question. This question is interesting, and I also have the same question. How do we interpret the symmetries matrix U? This is related to the MSR work you mentioned in your talk.
Yeah, so the symmetry matrix is essentially trying to indicate how different underlying parameters should be shared. And so each row in that symmetry matrix will indicate whether a parameter, what kind of parameter in the reparameterized matrix it should be using. And it may, if that matrix is binary, then it will just correspond to picking out which parameters to use, but it doesn't have to be binary, and it can actually kind of interpolate between different parameters to capture a more general class of equivariances. But essentially, it's governing how weights are shared in the reparameterized weight matrix.
Mm-hmm. So just a clarification on that. So do these of course, they depend on the tasks that are being meta-learned together, but do they also depend on the data and the network architecture?
You can apply MSR to a fully connected weight matrix. You can also apply it on top of a convolutional architecture, as I showed in one of the synthetic experiments. So in that sense, if you want to build in equivariance, like translational equivariance, for example, but learn other forms of equivariances, then in principle, you could apply this sort of reparameterization on top of other architectures. So in that sense, it can be kind of flexibly applied to different kinds of architectures, and will be dependent on the architecture to some degree. It also definitely depends on what data you put in. If you put in data that doesn't share, like a set of tasks or data corresponding to those tasks that don't share equivariances, then you won't get equivariances out.
Next question, I think, is about the same MSR method. Does the method work for very skewed data example? Yeah,
so in that work, we weren't looking at very skewed task distributions. Though in the adaptive risk minimization work, that method actually does work. We did test it, and it does work quite well on skewed distributions. I believe the federated extended MNIST dataset is one example of a skewed distribution. We also had a very explicitly skewed distribution in another experiment on the paper that looked at MNIST with different rotations. And it builds upon some of these ideas in distributional robustness that have also been successful with skewed data sets. And that's, in some ways, that's what the worst case group is evaluating. It's evaluating how well you can handle groups that are very underrepresented in your data.
Mm-hmm. Thank you. Next question is from Gamal, who's asking, for learning a low-rank, locally connected structure, how does the meta-learning approach perform compared to finding the rank of the locally connected structure by validation, as one of the paper in ICML 2020? And what is the advantage, pros and cons of one approach over another?
Yeah, so I'm familiar with that work, and I think we actually cited it in the ARM paper, and it inspired our low rank experiments that I showed on the second experiment that I showed. The problem setup is a little bit different. So in MSR, we assume that we have multiple tasks, whereas in the work, this ICML paper, it was looking at just a single task. I think the key distinguishing factor, though, is that MSR isn't specific to learning low-rank locally connected networks. It can also learn other forms of equivariances, such as rotation, reflection, and so forth. So it's essentially a more general approach for learning this sort of equivariant structure.
Mm-hmm. Another question from Siawash. The question is, meta-learning seems not to be that successful in cross-domain classification settings in comparison with transfer learning. So do you think this adaptive risk minimization works in large distribution shifts, like from ImageNet to Celeb A?
So in the adaptive risk minimization work, we didn't do anything specifically to try to address cross-domain transfer, so I wouldn't expect it to do any better than any other meta-learning method on that. I guess one example of this sort of cross-domain transfer is the metadata set work that was, I think, spearheaded by Hugo Larochelle and his collaborators. And there, I think we have seen some success with meta-learning methods. I think that one of the reasons why we haven't seen more success in those settings is that to do well on computer vision focused tasks, you don't necessarily need to learn a full kind of learning procedure. You need just a good representation. If you have a really good representation of images, then that already takes you a lot, like pretty far for solving image classification kinds of tasks. I think that other tasks similar to the ones that I mentioned before, where you want to do imitation learning, or you want to be able to do predictive properties of molecules and so forth, those sorts of things are ones where we've seen more success because it's more about actually adapting to data and less about learning a good feature representation.
Awesome. Olgert is asking, and this is a very fundamental question, I think. Is there a definition for what a task is? How do you define a task formally?
Yeah, so in my meta-learning course, I formally define a task to essentially be a data distribution, to be a distribution over like X and Y given X, or in the reinforcement learning case, a task may correspond just to an MDP. And different tasks may vary in different ways. So some tasks may share the same P of X, but have a different P of Y given X. This will correspond to things like maybe P of X is just kind of the distribution over all natural images, and P of Y given X is different ways that you want to label those natural images, for example. Whereas other settings may have a different P of X for different tasks, like the setting where you have different molecules. So that's kind of the formal way that I define a task, and it's much broader than the kind of English definition of the word task. It can cover different domains, different environments, really just can correspond to different machine learning problems. Of course, in practice, you don't have access to the true data generating distribution. Instead, for each task, you have access to a data set for each of those tasks. So yeah, that's the formal definition that we give, that I like to give to my students. Of course, all of these methods assume that your tasks all share some amount of structure, and formally defining what it means for tasks to share structure is also very challenging. For that, I actually like to look at Bayesian graphical models to define that, because it actually allows us to provide a nice formalism about how the data generating distribution depends on some shared latent variable. And if they are, if if there is no kind of underlying latent variable that generates these data generating distributions, then there is no kind of shared structure. If there is, kind of graphical models give you a framework for thinking about how tasks are structured and what sort of like independencies you might get as a result of that.
Mm-hmm, mm-hmm. Yeah, Isabel has a follow-up question on that particular definition. So do you not include objective in the task definition?
So yeah, I actually, that's a omission in my part. Typically, we do also include the objective as part of the task. Oftentimes, you can simply define the objective as like maximizing the log likelihood of the outputs given the inputs. That's a pretty common objective, but there are cases where you may want to optimize a different objective, and that would also be part of the formal task definition.
Nice. So now that we have this formal definition of task, how can we determine which tasks are more suitable to be meta-learned together?
Yeah, that's a really good question. And it also applies to things like multitask learning, where you're trying to train a single model on all of the tasks. And it's a question that I get a lot. And kind of another kind of framing of this question that I also hear a lot is, how do you measure whether two tasks are very similar? How do you understand kind of the distance between a pair of tasks, for example? And then if we could define that, maybe we could figure out how we might share share training for some tasks and not for other tasks. I think that this notion of kind of task similarity is very difficult to define. And the main reason for that is that I think that the similarity between two tasks won't just depend on those two tasks and their underlying data sets, but it's also going to depend on the knowledge that the model has already. So for example, in robotics, say that you have two tasks. One task is to grasp a cup and pour, and another task is to maybe grasp a pen and write. If you don't yet know how to grasp, then these tasks may look somewhat similar because they'll both teach you about grasping. Whereas if your model already knows how to grasp, pouring and like writing some letters may look extremely different. So I think that our notion of similarity between different tasks needs to inherently depend on the current model and its underlying knowledge in order to just somehow define whether or not sharing information and knowledge across those tasks will be useful for future learning. Mm-hmm. So we have some recent work that isn't quite public yet that's looking at trying to quantify this notion of transfer between tasks in a way that actually depends on the model itself. And yeah, so you can look out for that work in the future.
Super. I work in industry as a practitioner. I'm more worried about getting the best out of my models, right? And so then I have to think about all the trade-offs. Do I create a standalone model? Do fine tuning, or do transfer learning, do multitask learning, or do meta learning? And that's kind of motivated this question. Also, one of the focus in meta learning research seems to be how we can learn fast with fewer examples and maybe fewer gradient updates and so on. But in many settings in industry, more than learning fast, how can we learn better is a focus. Is there any way so that we can say that the meta learning would just be better than all other competing approaches without really having to go through a lot of trial and error kind of experimentations to figure out what works, what not?
So I think that you can define learning better in a couple of different ways. One is one way to look at it would be like training and generalization. Can I get to the bottom of my kind of training objective with maybe fewer gradient steps, or get to a better optimum of my training data set?
The latter is the one that I mentioned, yeah, the better optimum.
And the latter would be, can I kind of generalize better in some way, get a model that achieves better like generalization performance? For the latter, we need to, if we care about the former, I think that's kind of more about building better optimizers. And there is actually a lot of work in kind of AutoML and hyperparameter optimization and so forth that focus a lot on building better optimizers. In terms of getting better generalization, to do that, what we really want to look for is something that allows us to restrict our hypothesis class to and kind of encode some inductive biases from the previous data that we've seen that allows us to generalize further. If we don't change the hypothesis class in any way, if we don't introduce any bias, then we won't be able to that our optimizer won't be able to generalize better than if we were just training from scratch. And I think that in many ways, meta-learning algorithms do, including few-shot meta-learning algorithms, do address this latter point. They focus a lot on generalization typically from a small amount of data. I do think that there is, though, this kind of open question about, like, what about the medium shot setting? What if you have like a couple hundred data points or 1,000 data points or something? In those cases, we haven't really seen benefits from meta-learning compared to something like fine-tuning. Fine-tuning seems to be like a really strong approach for doing something like that. And I think it's still an open question for whether the challenges there are arising from like computational challenges, because in meta-learning, typically we use a truncated inner optimization because it's just like computationally easier to do that, or if it's something kind of more fundamental to the algorithms that we're developing.
Great. Thank you very much, Chelsea. I don't think we have any more questions remaining. If you have any final remarks that you would like to make to the audience, please go ahead.
Yeah, I think that I don't have any major final remarks other than the kind of main takeaways of my talk of trying to really think critically about how we actually develop machine learning systems that aren't just a static model deployed in a world that's constantly changing around them. I think we need to think fundamentally about what is the right problem statement that can capture this sort of challenge. And also, of course, think critically about what are the best ways to handle distribution shift. Inherently, if we want to tackle problems in generalization and distribution shift, we're going to need to introduce additional assumptions. We know that empirical risk minimization, like, it will work if the training and test distributions are the same. If they're not, like, we can't really say anything about how it will do. So this points us to thinking about additional assumptions. I think that there are probably a lot of additional assumptions that we can introduce that are pretty mild, but we need to think critically about what those assumptions should look like. I think that our development of these problem statements should really be informed by problems in industry, by real world problems that people are facing, and try to bring those problems into machine learning so that we can hopefully get over this hump of models that just kind of do well on the distribution that they're trained on.
Perfect. Thank you very much, Chelsea. That would be it for the keynote today. Thank you very much for your time. It was really fantastic keynote. I really enjoyed that a lot.